Hello everyone, I am Bireshwar Roy. I am currently pursuing my 4th year PhD in the Department of Physics, Indian Institute of Science, Bangalore. In this NPTEL GATE Physics course, I will be discussing some previous year's GATE Physics questions and try to solve them with proper explanations. This question was asked from the GATE Physics paper 2021. There is a MCQ type 2 marks question and the topic of the question is quantum mechanics. The question is, consider a spin is equals to h cut by 2 particle in the state phi. In the matrix form it is 1 by 3 2 plus I 2. The probability that a measurement finds the state with Sx, that is x component of the spin, equals to plus h cut by 2 is option A 5 by 18, option B 11 by 18, option C 15 by 18 and option D 17 by 18. Let us see the solution part now. It is given in the question that the wave function of a spin-half particle, that is S equals to h cut by 2, is phi before the measurement, and the phi state is 1 by 3 times this column matrix, that is 2 plus I 2. We have to find the probability of getting an eigenstate of Sx with eigenvalue plus h cut by 2 after doing a measurement of x component of spin on that particle. Now we know spin angular momentum of a particle has three components. Those are Sx, Sy and Sz. These components are actually known as spin operators for the particle state. These operators can be represented as 2 cross 2 matrix for spin half particle. The Sx operator is represented as h cut by 2 times 0 1 1 0, and this operator has the eigenvalues plus h cut by 2 minus h cut by 2, and corresponding eigenstates are 1 by root 2 1 1 and 1 by root 2 1 minus 1 respectively. Similarly, the Sy operator is represented as h cut by 2 times this matrix 0 minus I 0. Corresponding eigenvalues are plus h cut by 2 minus h cut by 2, and for this eigenvalue plus h cut by 2 we will have a eigenstate 1 by root 2 1 I, and the eigenstate corresponding to the eigenvalue minus h cut by 2 is 1 by root 2 1 minus I. And the spin operator Sz has the form h cut by 2 times this matrix 1 0 0 minus 1. Eigenvalues are plus h cut by 2 minus h cut by 2, and corresponding eigenstates are 1 0 and 0 1 respectively. These three matrices are known as Pauli matrices. We have already seen that each spin operator will have two eigenstates with eigenvalues plus h cut by 2 and minus h cut by 2. According to our question, we have the final state as the eigenstate of Sx operator with eigenvalue plus h cut by 2. So from now we will deal with the eigenstate of Sx operator. So there are two eigenstates of Sx operator that we have already seen in the previous slide. Those are, so first eigenstate is chi plus, that is 1 by root 2 1 1, and it has the eigenvalue plus h cut by 2. The another eigenstate of Sx operator is chi minus, that is 1 by root 2 times this column matrix 1 minus 1, and it has the eigenvalue minus h cut by 2. So after doing the measurement on phi state, we'll get this chi plus state as the final state with the eigenvalue plus h cut by 2 with some probability. So we have to find that probability of getting this chi plus state as final state. In order to find the probability, what we will do, we'll take the inner product between this final state chi plus state and the initial state, that is phi state, and after that we will take the mod square of that inner product. So let us do that operation. So the probability will be mod square of this inner product chi plus and phi state. Now this is in the bracket notation. So bra of chi plus is basically complex conjugate of this kate of chi plus. So if we take the complex conjugate of this matrix, then it will be 1 by root 2 times this row matrix 1 1, and this matrix is multiplied with the kate of phi. So that is given in the question 1 by 3 times 2 plus I 2, and we have to take the mod square of this matrix multiplication. So if we just take out this 1 by 3 and 1 by root 2 from this modulus, then we will get 1 by 3 root 2 whole square times mod of multiplication of these two matrix 1 1 2 plus I 2. So if we just do the multiplication of between these two matrix, so we will get 1 times 2 plus I plus 1 times 2. So that will basically lead to 4 plus I, and this 1 by 3 root 2 whole square is basically 1 by 18. Now mod of 4 plus I basically root over 4 square plus 1 square. So that is root 17, and we have to take square of that. So it will finally give 17 by 18. So the probability of getting the eigenstate of Sx with eigenvalue plus h cut by 2 after doing the measurement is 17 by 18. So our option D is correct. So according to our solution, the probability that a measurement finds the state with Sx equals to plus h cut by 2 is option D, that is 17 by 18. This question was asked in the GATE Physics paper 2021. This is a numerical answer type 1 marks question, and the topic of the question is solid state physics. Specifically, it was asked from the chapter semiconductor physics. The question is, the donor concentration in a sample of n-type silicon is increased by a factor of 100. Assuming the sample to be non-degenerate, the shift in the Fermi level in milli-electron volt at 300 Kelvin rounded off to the nearest integer is, so some information has been given, that is Kb times T equals to 25 milli-electron volt at 300 Kelvin. So let us see the solution part now. We know in an intrinsic semiconductor, the electron density N in the conduction band and the hole density in valence band is equal, and that is denoted by Ni, where Ni is the intrinsic carrier density. Now, Fermi level for this type of intrinsic semiconductor is given by intrinsic Fermi level Ei equals to Ec plus Ev divided by 2 plus 3 by 4 kBt times ln of mp star by mn star, where Ec is the energy at the conduction bandage, Ev is the energy at the valence bandage, T is the absolute temperature of this semiconductor, mp star is the effective mass of the hole in the valence band, and mn star is the effective mass of the electrons in the conduction band. So from the diagram we can see the intrinsic Fermi level will lie in between the Ec and Ev energy level. If we perform external doping in intrinsic semiconductor, then it is known as doped semiconductor or extrinsic semiconductor. Depending on the type of impurity doped in the semiconductor, it is classified as two types. First one is N-type semiconductor and the second one is P-type semiconductor. In the N-type semiconductor, the doped impurity acts as donor of electrons in the conduction band. Hence, the electron density in the N-type semiconductor will be increased. But in p-type semiconductor, the doped impurity acts as acceptor of electrons from the valence band. So here the hole density will be enhanced in p-type semiconductor. If we see the band diagram of n-type semiconductor, the donor energy level Ed will lie above the intrinsic Fermi level Ei. At 0 Kelvin temperature, all the donors are in the unionized state. That is, all the donor levels are occupied with electrons. As temperature increases slightly, some of the donors get ionized and contribute electrons to the conduction band. Also, some of the electrons from the valence band will jump to the conduction band, and it will leave behind some holes in the valence band. The number of holes produced in this process is very small. Therefore, the Fermi level in the n-type semiconductor EF must lie somewhere near the middle of the donor level and the bottom of the conduction band, that is EC. Similarly, in p-type of semiconductor, the acceptor level EA will lie below the intrinsic Fermi level, and the actual Fermi level for the p-type semiconductor, that is EF, will lie in between EA energy level and EV energy level. But at sufficiently high temperature like room temperature, the donors or the acceptors will get completely ionized. So that is complete ionization. So for n-type semiconductor, the impurity type is donor of electrons. At sufficiently high temperature, all the donors will be ionized. So for the case of complete ionization, the concentration of donor atoms is given by Nd equals to Nc times exponential of minus Ec minus Ef divided by kBt, where Nc is 2 times 2 pi Mn star kBt by h square whole to the power 3 by 2. Here Nc is known as effective density of states of electrons at the conduction band edge, that is at energy level Ec. If we just take the logarithm on both sides and after some rearrangement, we'll get the Fermi level of n-type semiconductor as Ec plus kBt times ln of Nd by Nc. Now at a particular temperature, the Nc is constant, so the EF energy level will depend on only the donor concentration, that is Nd. As Nd increases, the EF energy level of the n-type semiconductor will increase. In the previous slide, we have already seen the Fermi level of the n-type semiconductor will depend on the concentration of donor atoms doped in that semiconductor. Now, according to the question, we will consider two cases. In the first semiconductor, the donor concentration is Nd and the Fermi level is at EF1. And in the second semiconductor, n-type semiconductor, the concentration of donor is 100 times Nd and the Fermi level will lie at EF2. As the donor concentration in the second type semiconductor is greater than the first semiconductor, so obviously the EF2 will be greater than EF1. So we have to basically calculate this difference, that is EF2 minus EF1, which is difference of the Fermi level of these two semiconductors. Also, some informations are given. We have to consider the situation at temperature 300 Kelvin and the thermal energy is given by 25 millielectron volt. Now, we will directly use the formula for Fermi level in n-type semiconductor for both the cases. In case 1, the Fermi level EF1 is equal to Ec plus kBt times ln of Nd1 by Nc, where Nd1 is the donor concentration in the first n-type semiconductor. For the second n-type semiconductor, where the doping concentration is increased by 100 times, the Fermi level EF2 is Ec plus kBt times ln of Nd2 by Nc. Here Nd2 is 100 times of Nd1. So the shift in Fermi level due to the increase in doping concentration by 100 times, the del EF is given by EF2 minus EF1, which is kBt times ln of Nd2 by Nc minus ln of Nd1 by Nc. So del EF equals to kBt times ln of Nd2 by Nd1. Now Nd2 is 100 types of Nd1, so kBt will be ln of 100 Nd divided by Nd. So Nd will cancel out from the numerator and denominator. So del EF will be kBt times ln of 100. Now at temperature 300 Kelvin, the kBt, that is thermal energy value, is 25 millielectron volt. So if we put that kBt value, we'll get del EF 25 times ln of 100 millielectron volt. So our del EF will be around 115 millielectron volt, and this is the final answer for this question. According to our solution, the shift in the Fermi level in millielectron volt at 300 Kelvin is 115 in the integer form. This question was asked from the GATE Physics paper 2021. This is a MCQ type 2 marks question, and this question was asked from the topic Quantum Mechanics. The question is, consider a particle in a one-dimensional infinite potential well with its walls at x equals to 0 and x equals to L. The system is perturbed as shown in the figure. So in the figure it has been shown a particle in a one-dimensional infinite potential well. In addition to that, we have a perturbed potential which is varying linearly from x equals to 0 to x equals to L. At x equals to 0, the perturbed potential has value 0, and at x equals to L, the perturbed potential has the value V0. We have to find the first order correction to the energy eigenvalue. There are 4 options given. First option is option A, V0 by 4, option B, V0 by 3, option C, V0 by 2, and the last option D, V0 by 5. Let us see how to solve this problem. We are given a particle in an one-dimensional infinite potential well with its walls at x equals to 0 and x equals to L. In addition to that, we have a perturbed potential that is varying from x equals to 0 to x equals to L in that system. We are asked to find the first order energy correction to the energy eigenvalue of this particle in that infinite potential well in presence of the perturbed potential. In order to solve this problem, we will use the time independent perturbation theory. In time independent perturbation theory, we first solve the unperturbed system to find the eigenstates and the energy eigenvalues. Then we take the expectation value of the perturbed potential with respect to the unperturbed eigenstates or the wave function of that system to find the first order energy correction in that system. So let us see what is the unperturbed states in this case. So this is very well known problem, that is a particle in a infinite potential well which can be exactly solved by using the Schrodinger equation. So by solving the Schrodinger equation, we can find the eigenstate or the eigenwave function of this system, and this is given by psi nx equals to root over 2 by L times sine n pi x by L, where n corresponds to the init state of this particle in that infinite potential well and L is the separation between the walls in that system. We already know about the wave function or the eigenstate of the particle in the unperturbed system. Now we will include the perturbation which is varying linearly from x equals to 0 to x equals to L. So the perturbed potential will have the form A plus bx, which is the equation of straight line. So we will apply the boundary conditions of the perturbed potential to find the coefficient A and B in that equation. So at x equals to 0, this perturbed potential is 0. So basically it will give A equals to 0. at x equals to L, this parted potential has the value V0. So we'll have V0 equals to B times L, and our A is 0 from the first boundary condition. So basically it will give P equals to V0 by L. So if we put that A equals to 0 and B equals to V0 by L in that equation, then we will get the parted potential as Vpx equals to V0 by L times x. Till now, we already know about the wave function of the unperturbed system and the form of the perturbation or the parted potential in that system. Now we have already discussed how to find the first order correction to the energy eigenvalue in presence of the parted potential. So this is actually we have to take the expectation value of the parted potential with respect to the unperturbed wave function of that system. So this is given by En1, which is the first order energy correction, equals to this expectation value of the Vpx with respect to the psi nx, which is the unperturbed wave function of that system. So now our psi nx is basically root over 2 by L times sine n pi x by L, and our parted potential Vpx equals to V0 by L times x. So we will just convert this bracket notation to the integration form. So this will basically give your Vpx times psi n square times dx and integration over 0 to L. So if we just put the psi nx and Vpx in that integration, so we will get 2 by L times V0 by L times integration 0 to L x sine square n pi x by L times dx. Now we will take this 2 inside the integration. So this will basically give this 2 sine square n pi x by L. Now we know 2 sine square theta equals to 1 minus cos 2 theta. So we will just apply that trigonometric formula here. So this will give first order energy correction En1 equals to V0 by L square times integration 0 to L x times 1 minus cos 2 n pi x by L times dx. So basically now this integration is divided into two parts. So this will give V0 by L square times integration of 0 to L x dx minus integration from 0 to L x cos 2 n pi x by L dx. Now from the previous equation we have to perform two integration. One was integration x dx from 0 to L, another one was integration 0 to L x cos 2 n pi x by L dx. So for the first integration we will have V0 by L square times x square by 2 from 0 to L, and for the second integration we have to apply the by parts rule. So this will give V0 by L square times x sine 2 n pi x by L whole divided by 2 n pi divided by L from 0 to L minus integration 0 to L sine 2 n pi x by L divided by 2 n pi by L times dx. So this term will basically give V0 by L square times L square by 2, and for this term we will have V0 by L square times 0. So basically for at x equals to L, this will give sine 2 n pi, which is 0, and x equals to 0, this whole term x sine 2 n pi x by L will be 0. So effectively it will give 0, and we have to perform this integration again. So this will give L by 2 n pi times minus cos 2 n pi x by L whole divided by 2 n pi by L from 0 to L. So this term will give V0 by 2, and we have plus V0 by L square times L square by 2 n pi whole square times at x equals to L it will give cos 2 n pi, and x equals to 0 it will give cos 0. Now cos 2 n pi is 1 for any integer value of n, and cos 0 is 1. So effectively this term will give 0. So our first order energy correction will be V0 by 2. So our option C is correct for this question. From our solution we found that the first order correction to the energy eigenvalue is option C, that is V0 by 2.